video, I had discussed about linear transformation. I had seen let V and W be vector space. Then the mapping T from V to W is called linear transformation if T of x plus y equal to T of x plus y and T of alpha x equal to alpha times T of x, where for all x belongs to B and for all alpha belongs to the field A. And this is the picture of linear transformation. Here I have considered V and W be different vector spaces, and when V equal to W, then the linear transformation is called as linear operator. Means linear operator B, special case of linear transformation. And today's goal of this lecture is to find kernel and range of linear transformation. That means we will see the new notation kernel and range of linear transformation. Then our next goal is when a linear transformation be 1, 1 and on 2, because linear transformation be a function and 1, 1 and on 2 related on this idea kernel and range. Then our goal is how kernel and range related with non-homogeneous equation Ax equal to B. And this goal is very important because every finite dimensional linear transformation can be written as Tx equal to A times x. Okay? Well. Now let's see what is the kernel and range of linear transformation. Consider a linear transformation T from V to W. Then kernel equal to set up those U in the vector space V such that Tu equal to 0 vector. That means kernel is set up those subset in V such that this subset map 0 vector, and range is set up those element Tx which is member of obviously W. That means image of this transformation is actually called as range, where x be the member of V and this kernel is actually, since this is subset of V, this is actually subspace of the vector space V, where T be a linear transformation from V to W. How this is subspace of the vector space V? Let's verify. To prove subspace of the vector space V, at first we have to prove is kernel of T is non-empty? Obviously, because T of 0 V always equal to 0 W. That means 0 element is always belongs to kernel T. Next property, is kernel of T closed under vector addition? See, let x and y be two arbitrary elements of kernel T. Then T of x plus y by the property of linear transformation, this is equal to Tx plus Ty. And since xy belongs to kernel T, that means Tx equal to 0 vector and Ty equal to 0 vector. That means this is equal to 0 vector. And from this expression, it is true the vector x plus y belongs to kernel T. Okay? Next, we have to show is the kernel T closed under scalar multiplication? Consider x belongs to kernel T, then T of alpha x, obviously by the rules of linear transformation, alpha times Tx. And since x belongs to kernel T, that means Tx equal to 0. And this alpha times 0 equal to obviously 0. Therefore, since T of alpha x equal to 0, that means alpha x belongs to kernel T. Therefore, all condition of subspace has satisfied. So, kernel T always be subspace of the vector space V. Okay? Well, similar to kernel of linear transformation, image T, that means range of the function, is a subspace of the vector space W, where T be a linear transformation from V to W. This is the actual picture of, this is image of T, and this is kernel of T. And dimension of image T is actually rank of the linear transformation. Okay? Are you getting what is the rank of the linear transformation? Well, now I will prove image of the transformation is subspace. The image T is non-empty because T of 0 B equal to 0 W, that imply always 0 be member of image T. Now consider two arbitrary element W1 and W2 belongs to image T and alpha be any scalar. Then we have to show W1 plus W2 belongs to image T and alpha W1 belongs to image T. At first consider W1 belongs to image T, and W1 belongs to image T imply there exists V1 belongs to vector space such that TV1 equal to W1. Likewise, there exists V2 in the vector space V such that TV2 equal to W2. Now apply T on the vector space V1 plus V2. And by the property of linear transformation, this is equal to TV1 plus TV2. And TV1 equal to W1 and TV2 equal to W2. Now put this value, then this would be W1 plus W2. That means TV1 plus V2 equal to W1 plus W2. That implies W1 plus W2 belongs to image T. Therefore, one property has satisfied here. Second, T of alpha V1 equal to, by the property of linear transformation, alpha times TV1 and put the value, then this would be alpha times W1. Since T of alpha V1 equal to alpha W1, that means alpha W1 belongs to image T. Therefore, since W1 plus W2 belongs to image T and alpha W1 belongs to image T, that imply image T be a subspace of the vector space. Are you getting? Verify some example of kernel T and image T. First example, consider a mapping T from R3x to R2x. And the mapping is such type T of Px equal to P prime x. What would be the kernel T and image T of this linear transformation? To find kernel T, at first we have to find T Px equal to 0. That means, that implies P prime x equal to 0. And P prime x equal to 0 means all polynomial whose derivative P is 0. And all polynomial whose derivative P is 0, this is actually nothing but constant polynomial. So, kernel T equal to set of all constant polynomial. Are you getting how we have to find kernel T of linear transformation? Well. And what would be image T of this function? Just think. Here Tpx equal to P prime x. That means image would be first derivative of the polynomial. Here domain is R3x and codomain is R2x. That means first derivative of this polynomial would be obviously second degree polynomial. That means image T would be whole R2X. Okay? Well. Next example, TBA mapping from R2 to R2 such that Txy equal to 2x comma y. Here, since each component be linear, so obviously this mapping be linear. Are you getting? If you know the theorem, T from Rn to Rm be linear when each component be linear, then you can easily find linear transformation of any mapping. Okay? Now let's verify what is the kernel. Kernel means T of xy equal to here the vector 0 0 because this is mapped to R2. That means 2xy equal to 0 0. And 2xy equal to 0 0 imply x equal to 0 and y equal to 0. That means kernel T contain 0 0 vector. And image T equal to, notice T of xy equal to 2x comma y. That means image T equal to whole R2. Okay? Next example, linear transformation T from R2 to R2 such that T of xy equal to 2x comma 0. Obviously similar to before, this is linear transformation because all component be here linear, and kernel T equal to, notice here T of xy equal to 0 0. That means 2x comma 0 equal to 0 0, and from this expression obviously x equal to 0. And since here 0, that means y can be any number, y can be any arbitrary number. That means actually whole y-axis be kernel, because kernel be set of those elements 0 comma y where y belongs to R, and this is actually y-axis in R2. Okay? Well. And what would be the image of this transformation? Notice here T of xy is look like 2x comma 0. If you consider the element as u comma v, then when u comma v is same as 2x comma 0, when the element is look like x comma 0, where x belongs to any real number. That means this is nothing but this is actually the x-axis. That means kernel T is whole y-axis. Here whole y-axis mapped to 0 vector, and image of this transformation be whole x-axis. Okay? Now I will see interesting thing. Consider AB M cross N matrix and consider a linear transformation. Since here AB M cross N matrix, linear transformation for Rn to Rm such that T of x equal to Ax. Then what would be the kernel of this transformation? To find kernel, we have to find Tx equal to 0 vector. That means Ax equal to 0 vector. Ax equal to 0 vector, that means there exists a solution of this homogeneous equation, and we all of us know this solution is called as null space of the matrix A. Therefore kernel of this transformation is null space of the matrix A. Are you getting? Well, now I will see some nice property of range of a linear transformation. If V1, V2, Vk is the basis of the vector space V, then range of linear transformation spanned by tv1, tv2 up to tvk, and this set actually subspace of the vector space W. Are you getting? Well, consider a linear transformation T from P3R to P2R such that the defined transformation is as like Tpx equal to P double prime x minus 3p prime x. Here notice basis of P3R B. We all of us know 1x x square x cube. Then range would be of this transformation span of T1 comma Tx comma Tx square comma Tx cube, and T1 means just put the value P double prime 1 minus 3p prime 1. This obviously would be 0, and Tx means P double prime x minus 3p prime x. This would be minus 3, and Tx square means P double prime x square minus 3p prime x square. This would be 2 minus 6x, and Tx cube means P double prime x cube minus 3p prime x cube. This would be 6x minus 9x square. That means span of range T would be 0 minus 3, 2 minus 6x, 6x minus 9x square. Here notice 0 cannot be calculated because this is the span of this vector. That means this is the linear combination of this vector, and when the value of x would be 0, then obviously this would be 0, so 0 would be omitted. Therefore range T would be span of minus 3, 2 minus 6x and 6x minus 9x square. And here notice one interesting thing, these three vectors are linearly independent, because if we take these two vectors, then this vector not be combination of these two vectors. So obviously these three vectors be linearly independent. That means since range T span of these t vector which are linearly independent, so obviously dimension of range T is 3. Okay, and since dimension of range T is 3, and here the codomain is P2R, and we all of us know dimension of P2R is 3, so range T is actually whole P2R. Are you getting? Well, now let's see range of this transformation. Here for this transformation, range is span of TV1, TV2 up to TVN, where V1, V2, Vn be the basis of Rn. And we all of us know basis of Rn would be 1 0 0 0 0 1 0 0 up to 0 0 0 1 at the end component. Then range T would be span of A times 1 0 0, this would be TV1, TV2 would be A times 0 1 0 0, and TVN would be A times 0 0 1 at the end component, and A times 1 0 0 means actually this is the first column of this matrix, and this would be second column of this matrix, and this would be nth column of this matrix. Okay, that means range of this linear transformation is actually column space of the matrix. Are you getting? That means kernel of this transformation is null space of this matrix, and range of this transformation is column space of the matrix. And these types of example are more important for any competitive of exam. For next example, consider a linear transformation T from P2R to R4. Here polynomial of degree 2, that means T of a plus bx plus cx square equal to a plus b 0, a plus b, b plus c. Next, therefore, what is the image? Notice in P2R 1x x square be the basis for domain. Then T of 1 would be 1 0 1 0, T of x would be 1 0 1 1 and T of x square would be 0 0 0 1. Then image T would be span of T1 Tx and Tx square. And notice this vector is linear combination of these two vectors. Therefore, image T is span of these two linearly independent vectors 1 0 1 0 0 0 0 1. Since these two vectors are linearly independent, so image T span R2 and this is the subspace of R4. Are you getting the whole idea? Well, our next example, consider a transformation T from R2 to R3 such that T of alpha beta gamma equal to alpha minus 2 beta and beta plus gamma. Obviously this mapping be linear transformation because we can write it as Tx equal to Ax where A would be 2 cross 3 matrix whose each column be 1 0 minus 2 1 and 0 1. Since we can write it as Tx equal to Ax, therefore this transformation be linear and image T would be set of those elements such that alpha minus 2 beta and beta plus gamma where alpha beta gamma belongs to real number and alpha minus 2 beta beta plus gamma equal to, we can write it as alpha times 1 0 plus beta times minus 2 1 plus gamma times 0 1. That means since this vector is combination of these three vectors, that means image T is actually span of 1 0 minus 2 1 0 1. And since image T is column space of the matrix A and rank of transformation is equal to rank of the matrix A. Here notice this vector is linear combination of these two vectors. That means this vector is linearly dependent. That means image T is spanned by these two linearly independent vector 1 0 and 0 1. Okay, and dimension of image T is whole R2. Okay, and there exist a nice properties of Cardinality and image T. Let T be a linear transformation from V1 to V2. Then I have seen Cardinality is a subspace of V1. Also image T is a subspace of V1. Now I will see T is 1 1 when kernel of the linear transformation is only singleton set 0. And T is on 2 when image T equal to whole V2. In this example, here image T equal to whole R2. This linear transformation be on 2. Now I will see this proof. When T be 1 1, that imply kernelity also only contains singleton set 0. This proof is very easy type proof. At first, consider T is 1 1 and consider any element x belongs to kernelity. Since x belongs to kernelity, then by definition this implies Tx equal to 0 and 0 we can write it as T0. And since T is 1 1, since I have considered it, then consider this is Tx and this is Ty. Then Tx equal to Ty imply always x equal to y. That means x equal to 0. One side it has proved. When T is 1 1, then kernel T only contain singleton set 0. Conversely, let Cardinality equal to only contains singleton set 0 and consider Tx equal to Ty, and since T is linear, then that implies T times x minus y equal to 0 since T is linear. That implies x minus y belongs to card T, and since card T contains singleton set 0, that means from this expression we can tell x equal to y. Are we getting the proof? Oh, therefore, since I have considered Tx equal to y and I have got x equal to y, that means this transformation is obviously 1, 1. Consider a linear transformation T from R2 to R3 such that T of x equal to x1 plus x2, x1 minus x2, comma 0. Here x belongs to R2. Obviously this mapping is linear because each component be linear. Now, is this mapping is 1, 1? To check it, consider Tx equal to 0. And Tx equal to 0 imply x1 plus x2 equal to 0, x1 minus x2 equal to 0 and 0 equal to 0. And from this expression it implies x1 equal to x2 equal to 0. That means x equal to 0 vector. Therefore, Tx equal to 0 implies x equal to 0. That means this transformation is 1, 1. My next question, is this transformation is onto? No. Because if we consider E3 means 0, 0, 1 vector, for this vector we will get any image because here the image is look like here the third coordinate be 0, but here third coordinate be non-zero. So this mapping is not onto. So this is example of linear transformation which is 1, 1 but not onto. Okay. To find 1, 1 onto of the solution Ax equal to B is 1, 1 when pivot in every column of the matrix A and onto when pivot in every row of the matrix A. Because pivot in every column means there exists no free variable. So there exists only one solution. This is unique solution. So when every column is pivot, since there exists only one solution, unique solution, so this solution always would be 1, 1. Pivot in every row of the matrix imply obviously this space is onto, because when each row be pivot, consider this is here each row be pivot, then this is the solution Ax equal to here B. For every vector from output space there exists always a input vector. Okay. Consider one matrix whose every row not be pivot. Consider this row not be pivot. Then this is the solution of Ax equal to B. Then if this is non-zero solution, since in this row there is not pivot, so consider this row be 0, 0 row. So 0 equal to non-zero cannot possible. So for this non-zero value there exists no solution. So when pivot in each row of the matrix, then the solution Ax would be onto.